Welcome. Section Z.2. What we're going to be talking about is percentiles, z-scores, density curves, and the normal curve. Particularly, we're looking at really percentiles. Oh, sorry, that's not a pen. Percentiles, z-scores, and the normal curve. To give you an example just of something that you're used to, any standardized test that you guys have taken, when you get a report, a percentile is calculated based upon what is called a z-score. So, Z-score, that sort of being a super important thing is why we even called this chapter Z, because it is of utmost importance. So, jumping in a little bit, a density curve. A density curve is a curve that describes the overall pattern of data, the area that's underneath the curve, and above any interval of values on the horizontal axis is the proportion of all observations that fall in that interval. No real set of data is described by a density curve, but it is easy enough and accurate enough for practical use. So we're not really going to talk too heavily about really what density curves are, just sort of want that definition in there so that you have a little bit of a frame of reference. Normal distribution is described by a normal density curve. So this one is a specific type. And that's really what we're going to be interested in, the normal distribution, all of Z.2. Any particular normal distribution is described by two numbers, the mean and the standard deviation. So that's how we describe a normal distribution. The mean is at the center of the symmetric normal curve. So we don't have to worry about like skew left, skew right. If it's normal, it is symmetric, and the mean is at the center. And the standard deviation is the distance from the center to the change of curvature points on either side. So our mean, just when we're talking about the normal distribution, now we're going to talk about the mean being mu. So that's that Greek symbol or Greek letter, sorry, mu. And our standard deviation, lowercase sigma, which sort of looks like that. If we want to note, hey, we are working with a normal distribution with a given mean and a given standard deviation, it's written as n of mu and then the standard deviation. So this n is noting this is a normal distribution. The next number that follows is the mean and then the standard deviation. Many natural observations that we see in the world fall into a normal curve. Normal-like curve, I should switch those words. So standardized test results would be one example. So when we're talking about the normal curve, just to give you an idea over here, we're talking about something that looks like this, where you have a little bit happening on either end and then most happening in between. So a standardized test sort of mimics that. We have just a few people who are going to go so far beyond, a few people who are going to fall far behind, and then most of our people being somewhere in the middle. Repeated precise measurements will fall in that same category. If it's a repeated precise measurement, you're only going to have a few that are going to end up going to either extreme, and most of them will be right in that middle. So sort of important in something like manufacturing industry would be an example. And then just some biological properties would fall in this same category. So talking about sort of all of this, in a normal distribution with mean mu and standard deviation sigma, approximately 68%, so approximately 68% of observations will fall within, I don't know why I have an or there. It should say one, no ors here, just one standard deviation of the mean. Sorry about that. So again, just to look at what an image of our normal distribution is going to look like and help us explain this, we've had our horizontal line. And then I'm going to try and draw this well. That was pretty good. Wow, I'm impressed. Good work, me. So here we have this normal curve. If we say right dead center, we have our mean. So here we have mu, the mean, which looks a little bit like an M, so I want to switch that. So here we have mu. Okay, Yeah, I'm sorry, I'll stop. That's mu, the mean. 68% of all of your data is falling within one standard deviation. So I can go to a +1 standard deviation here, or to a -1 standard deviation here. And that's going to represent 68%, roughly 68%, of all of the observations. 95% of the observations are going to fall within 2 standard deviations. So now if I said here's 2 standard deviations, or -2 standard deviations, this encompasses, that's a not very good squiggly bracket, 95% of our data. And then last 3 standard deviations is 99.7. So right here, we have our +3 standard deviations or -3 standard deviations. And that's 99.7% of our data. So if we're looking at each one of these sections, then this would be 34% and 34%, since this total is 68. This would be an additional 13.5% and 13.5% to give us that total of 95. In that small little spot, we'll have I'll draw an arrow to it, 2.35% and 2.35%. And beyond 3 standard deviations, all you have left over is 0.15%. And a negative, not negative, just another 0.15%, giving you a total of 100% of your data, and sort of showing you that symmetry, the way that that's broken down. So we talked in Z.1 about finding the standard deviation of a data set. Now we're just saying what that standard deviation can do, for instance, in a normal curve, is say, or give, more so, an idea of how far away or what percentage you have done better than, or worse than, or whatever. So here, if I knew that the mean was some number like 0 and the standard deviation was 10, then this would be 0, 10. This would be 20 because it's 2 standard deviations away. This would be 30 because it's 3 standard deviations away, and so on and so forth. Next, what we want to talk about is percentile. So percentile, the way that we are going to define this is the pth percentile of a distribution is the value with p% of observations less than it. Observations less than it. So again, sort of thinking back to a standardized test, if you were told that you were in the 91st percentile, that would mean that you did better than 91% of people. So just to give 2 other examples, if I was talking about the 75th percentile, if we think about this on a normal curve, so our 75th percentile, somewhere around, let's say here, so that's P being 0.75, 0.75 meaning 75%. That would mean that 75% of observations are below that. If we talked about the 30th percentile, that means that your p-value is 0.3, and that's telling you again what percent fall below it. So 30th percentile would say maybe is here. So it's giving this area underneath this curve. That would be 30%. Again, P being 0.3, representing that 30%. So in a given problem with some context, how do we come up with that percentile? That's what we're really going to focus on. So we do that. Oh, sorry, I skipped just way far ahead. You guys were fine with all that. Z-scores is how we're going to do that. Don't worry if you don't have this table. I know it's not printed on your notes, but you'll get a copy of this table if you haven't yet. This table is a table where what you're going to do is find the Z-score for some given data. And all of these numbers inside here are p-values. So a z-score is a standardized value measuring how many standard deviations from the mean a particular point is. So the way that we calculate that is going to be z is equal to x minus the mean over the standard deviation. And a different way of writing that just symbolically is x minus mu over the standard deviation. So this is your formula for a z-score. Again, the point of a z-score is so that you can figure out, based off of the mean, based off of the standard deviation, what percentile you did better than, or the observations, what percentile were below that. So what I'm thinking about is like if we took a test, just a regular honors pre-calc test, I could give you the mean, I can give you the standard deviation. And from that alone, you can figure out what percent of students you did better than, because you would have your score minus the mean divided by the standard deviation. That would give you your z-score. Then, using your z-score, you would go to this table and match up, let's say our z was 0.98. We would come here to this 0.9 and then 0.8, so 0.90 or 0.9 and then 8. So that would mean that you did better than 83.65% of students. So it's a pretty nifty thing. We're going to go over just 3 examples of using this, really 2. This one is going to be a little bit different. But I strongly recommend, I'll try and make those examples super quick, but also thorough. And you want to make sure that you know how to read one of these tables. Calculating the z-score and interpreting the z-score, that's sort of the whole goal here, is that you can do that. So either watch it in class with us, or watch it now, or do both, be a real go-getter. Good luck.